Good evening, everyone. So this is the first lecture after so many days. I'm starting again the signal systems. So I already discussed the introduction of two, that is basic types of signals, etc. from the chapter 1. Similarly, we discussed the LTI systems. And in this we have known what is the convolution, what are the LTI system properties. This is introduction to signals and systems, right? Some different types of signals, right? So from this, so we may get one or maximum two questions in the gate, right? There is no doubt at all. So in this gate 2017 also we got one question from the systems, that is find the stability, etc., right? And some other question set. We got one more question from the energy and power formula, something like that, right? So we may get one maximum two questions we'll get in gate exam, right? Now I know, so we are lagging behind the schedule actually. So signals and systems should be completed by the March end only, but so due to some problems, so I am not unable to cover. So but from today onwards, that is this is the 12th for 2017, right? So by this end of this month, that is mostly 20 days I will take, or maximum. So I will cover by the 30th April 2017 this signals and systems course, right? So from May 1st we will start the EDC again, the different subject, right? So now we will start the Fourier series. So before the starting the Fourier series, we need some background, that is why we need to study this Fourier series and what is the outcome of this Fourier concept, Fourier series concept. Now, so up to now, this introduction under this LTI system, we know what is the different types of signals in the physical domain, and what is the system, right? System, and what is the system response, or if I give some input, how to get the output. Now, but so this we use this convolution procedure, etc. So it's very difficult to find the output responses for the different types of signals, right? So the convolution process will be somewhat the complex when we do some different suppose some periodic signals are given or some different signals are given. So it's very complex to find the convolution or to find the output response. Now, so we need a mathematical tool, right? So some mathematical tools, right? So it may be different transforms or a Fourier series, etc., to find the response of the system. So that is, suppose I'm having a system which is LTI system, that is linear time invariant system, right? So why we always say the linear time invariant system? So why another systems are not useful? Because see, whenever we are giving some input to any system, the output should be in terms of, it should be proportional to x of t. Then that system is a very reliable system, or we can say a better system. Now, and it should be time invariant. That means depending on the time, the response or the behavior of the system should not change, right? So it should be independent of time, right? So that is a linear time invariant system. So if I give some any input signal, it may be continuous, it may be discrete. Now what is the system response and how the behavior of the system response to produce the continuous output signal or discrete time output signal. Now we need this LTI system's response, how the behavior of this response, right? So how we can find the response of this system, what is the behavior, how to analyze. See, the main thing is how to analyze the system response, right? So what is the behavior, how if I give some sinusoidal signal or any step signal or any signal, right, which is available in physical domain. Now what is the output response depending on this LTI system response, or what is the analysis of this response, right? So to do this analysis we need some mathematical tools, right? So these mathematical tools are something like Fourier series, Fourier transforms, Laplace transform, Z transform, etc., right? So these are the different mathematical tools to analyze the system performance or system response, right? So that is the why we need to study the Fourier series. So we need to analyze the system response, right? So when we give some input signal, how to get the, or what is the output depending on the system response, right? Similarly, what is the outcome of this concept is, that is Fourier series. Now I am telling now the Fourier series is not a, this is not a transformations, right? So the transforms, actually the transform means we should convert one domain to another domain, right? So example is, suppose time domain to frequency domain, right? So that is the transforms, actually Fourier transform, Laplace transform, Z transform. Fourier series is not a transform, it's a just a representation of signals in some Fourier series expansions, right? So remember, Fourier series is not a transformation, it is just representing a continuous signals in continuous domain only. So it is in the Fourier series nothing but time domain to time domain only, right? The coefficients may be in discrete, that we'll see later. So the outcome of this concept is we can able to represent some any x of t, which is a periodic, into Fourier series representation, and we will get what are the different types of Fourier coefficients, right? So that is the outcome of this one, Fourier coefficients. Now, so what is the weightage of this this Fourier series in GATE is, so in GATE 2016 we did not get any question from this Fourier series, but in GATE 2017 we got one question for 1 mark, right? So the maximum we may expect from each set maybe one question from the Fourier series, right? So this is about some introduction about this Fourier series and what is the outcome of this Fourier series concept. Now we will start the, so what is the Fourier series and what is the how to find the Fourier series of the different types of signals. Now the Fourier series after, so the Fourier, so JBJ Fourier is a scientist who has done so much research from this mathematical tool. So he said any periodic signal x of t can be represented as weighted sum of harmonically related complex exponentials, right? So here any periodic signal, so remember this point, any periodic signal, this x of t can be represented as weighted sum of harmonically related complex exponentials. So we have seen what is the complex exponential and what is this harmonic and what is the weighted sum. See, also we can say linear sum of sums of the harmonically related complex exponential. Now before we start this the Fourier series, what is the harmonics and what is the complex exponential, first we will define what is a periodic signal, right? So we know we already discussed in this introduction to signals, what is a periodic signal is any signal, suppose x of t is there, if it is repeated after this time period harmonically, or if it is repeated for a time period t, this is here for all t, right? If it is satisfies this expression, so we can say x of t is a periodic signal. So example I can take like this, some minus t by 2 to suppose t by 2, and it is something like this, etc., and this is t, right? If you see here from 0 to this t, and the next it will be same, right, etc. So this is suppose x of t, and for every time period t, so it will be repeated after time period t, so here also, etc., right? So this is a periodic signal x of t, and here this time period capital T is called the time period of the signal, time period, right? So this is time period. So this can be written in this in terms of angular frequency, omega is equal to 2 pi by t, right? So as we know, this can be written as 2 pi f. So what is f here? F is equal to 1 by time period t, right? So this is a periodic signal x of t. Now we will see what is this harmonic relatively complex exponential. So from this Fourier series he said, so any signal x of t can be written the weighted sum, that is x of t is equal to, suppose, sigma, right, sum k is equal to minus infinity to infinity, right. So weighted sums, right. So I will assume the ak, which is the weight, and it will be represented by the complex exponential. So this j k omega naught t, right. So what is omega naught here is, this is the angular frequency or the frequency of fundamental frequency or the time period with respect to time period. So omega naught is equal to 2 pi by t here, right. So this is the equation of Fourier series. So any signal x of t can be represented by the weighted sum of the complex exponential, right. Now complex exponential is what? Suppose e power j omega naught t is there. So it is a periodic signal. It's a periodic signal with fundamental frequency as omega naught. So what is the fundamental frequency? Fundamental frequency is omega naught. Now what is this harmonics of this one is? Suppose at omega 2 omega naught, 3 omega naught, 4 omega naught, etc. These are the harmonics of this fundamental frequency, right. So if it is g power j2 into omega naught, g3 omega naught, is all harmonics, right. Now this is generally, we say this is a complex exponentials, right. So this can be written as cos omega naught t plus j sin omega naught t, which is a complex, right. So that's why it is a called complex exponential. Now if I expand this one, so what is this x of t can be written as? Suppose I will come with some a minus 2 e power minus j, so k is 2, so e power minus j 2 omega naught t plus a minus e power minus j omega naught t plus a naught into e power j0, so it will become 1 plus a1 e power j omega naught t plus a2 e power j 2 omega naught t, and so on. So this is the x of t can be written, see here, weighted sums. See, this is the weight and this is the complex exponential, so it may be harmonics, that is second harmonic, and this is the first harmonic, then this is some DC value, then again it is a first harmonic in the positive frequency, second harmonic. See, linear sums of this complex exponential, or we can say weighted sums. So we need to sum all the fundamental frequencies as well as the harmonics, then so this x of t can be represented by like this, the weighted sum of complex exponential signals, right. So this is the Fourier series expansions, right. Now we will find the Fourier series coefficients, right. So this is already we know, that is x of t is equal to sigma k is equal to minus infinity to infinity ak e power jk omega naught t. So what is this? It's a Fourier series representation of periodic signal x of t, and here this ak is called exponential Fourier series coefficients, right. So this can be written easily, but how to find this exponential Fourier series coefficients, that we need to find. Now if we assume this is equation 1, now what we need to do is, so we have to multiply with some e power minus j n omega naught t both sides, right. So that is, so it will become x of t into e power minus j n omega naught t is equal to sigma k is equal to minus infinity to infinity ak into e power jk omega naught t into e power minus jn omega naught t. So see here, j omega naught t is common, so this equation will become k is equal to minus infinity to infinity ak e power j k minus n omega naught t. So omega naught t, j is common, so k minus n. So this is x of t into e power minus jn omega naught t. So suppose this is equation 2. Now what we need to do is to find this ak, so integrate both sides over 1 period t. So what we need to do, so we need to integrate over single period, that is period means, so I will represent as single period means t, right? So that means it may be minus t by 2 to t by 2, 0 to t, etc. So over a single period, so that is t. So it will become x of t into e power minus jn omega naught t dt is equal to, if you see these two are the constants, right? With respect to 2 means, so it will be constant. So it will become k is equal to minus infinity to infinity ak into integration of, so we need to integrate over single period t. So it will become e power j into k minus n omega naught t into dt, right? So we need this integration term. So how to find? So I'll take separately this one, that is like this. So integration over single period t e power j k minus n omega naught t dt. If you see, if I integrate, suppose if k is not equal to n, right? So if it is, this is 2, this is 1, etc. So this term will become, see here, if it is not equal to n, so it will become integration over one period. So it will become e power j some constant, suppose I will take m omega naught t dt. So what is it? Will become integration over one period. So it will become cos m omega naught t plus j sin omega n m omega naught t. Now this already we know, if we integrate any cos signal or sin signal over one period, so it will become 0, right? If this is k is not equal to n, if k is equal to n, if k is equal to 1 n, so what we will get? Integration over one period e power j into k is equal to n means we will get 0 omega naught t dt. So what we will get? So it's a 1 means, so we'll get, so integration means constant over a single period means just suppose 0 to t, so we'll get the time period t. If it is a minus t by 2 t by 2, so it will become, this is actually t, not constant, t other r minus t by 2 t by 2 over a single period. So again it will become t. That means when, if k is equal to n, we will get this total integration as t. If it not equal to n, it's 0. So I will write like this, over period if I integrate e power j k minus n omega naught t dt is equal to t when k is equal to n, 0 when k is not equal to n. So we have to assume k is equal to n. So this equation, so it will become like this. Here integration, say, over one period, and this is x of t e power minus j n omega naught t dt is equal to sigma k equal to minus infinity to infinity ak into t. So this ak is a constant, so we said k is equal to n, we need to take. So this total will become some constant an. So an or which is equal to ak is equal to simply 1 by t integration of over single period t x of t into e power minus jk omega naught t dt. So this is how to find the Fourier series coefficient or exponential Fourier series coefficients. So 1 by t over single period, so we need to integrate the single period with x of t into e power minus jk omega naught t dt. Now we will solve one example problem. Now find the Fourier coefficients of given signal x of t. Now see, if you see this one, it's a periodic signal x of t. Now we need to, so what is the fundamental period? So it is 0 to t. Now, so what is the Fourier series coefficients? ak is equal to 1 by t over single period t x of t into e power minus jk omega naught t dt. Now how to find this one? So if you see the time period, so we need to integrate from 0 to t1 and again 0 to t, right? So better if I integrate from minus t by 2 to t by 2, again it is a single over one period only. So you will get from minus t1 to t1 only the value is there here, and the remaining here and here is a 0. So I will integrate like this. The time period is again t only, so I will integrate minus t1 or minus, first I will write like this, t by 2 to t by t and x of t into e power minus jk omega naught t dt. So minus t by 2 to t by 2, if I see, so here there is no value, so I will make it as minus t1 to t1. So 1 by t integral minus t1 to t1, x of t is in this region 1 into e power minus jk omega naught t dt. So 1 means 1 only. So integration of e power x is nothing but e power x only. So e power minus jk omega naught t by, so I assume this is x, so we need to differentiate again here. So minus jk omega naught into differentiation of t is 1. So what is the limits? Minus t1 to t1. So this will become ak is equal to 1 by t. This is e power minus jk omega naught. If I replace here in place of t, t1, so it will become t1 by minus jk omega naught minus e power, see minus t1 minus it will become plus jk omega naught t1 by minus jk omega naught, right? So this is overall. So 1 by t, see here jk omega naught is common, and say minus minus it will become plus, so it will be e power jk omega naught t1 minus e power minus jk omega naught t1. Now from this Euler's formula, e power j theta minus e power minus j theta by 2j means it is sine theta. So here j is there, 2 is not there, so it will be 2 by t, k omega naught is common, so it will be k omega naught into, I will write sine k omega naught t1 here, this is t1, right? So 2 by, this is the ak. Now again, so this is t here, this is omega naught. So omega naught is nothing but 2 pi by t. If I replace here 2 pi by t, t cancel, 2 will be cancelled, so it will become sine k omega naught t1 by pi, see k, pi k. This is the Fourier series coefficients of the given sequence, right? Now we will try to find this Fourier coefficients with respect to some time period. Suppose if I take this capital T, the time period is equal to 4 times of t1, so which is we got here. So this is 4 times of t1 means if I substitute here, that is omega naught into t1, it will become 2 pi by this t into t1, right? So omega naught is replaced by 2 pi by t. So what is t here? 4t1. So this will become 2 pi by 4 into t1 into t1. So t1 cancel, and this will become simply pi by 2 is omega naught t1. So this expression will become ak is equal to sine, so k into pi by 2 by k pi. Now here k cannot be 0, because if k is equal to 0, this will become infinity, right? So other than the k equal to 0, we'll get the Fourier series coefficients. So we'll 1 by 1, k is equal to 1. So what is a1 is equal to sine pi by 2 by pi. What is sine pi by 2 is 90 degree. Sine 90 means 1, so it will become 1 by pi. Similarly, k is equal to 2. So that is a2 is equal to sine 2 pi by 2, so it will become sine pi by sine 2 pi. What is sine pi? Is nothing but 0. Similarly, suppose k is equal to 3, so this will become sine 3 pi by 2 by 3 pi. So sine 90, so this is 3 pi by 2 means what? So 3 into 180, so it will become, I think 270 degrees. So it is minus 1 by 3 pi. Sine 3 pi by 2 is nothing but minus 1. Similarly, k is equal to 4. So sine, so 4 pi means you will get sine 2 pi by 4 pi. Again it will be 0. Similarly, suppose if I substitute k is equal to minus 1, so it will become sine minus pi by 2 by minus pi. So minus sine 90 means sine again 1, so but sine minus theta is become minus sine theta, so minus 1 by minus pi, again it is 1 by pi. That means if you see, we are getting one time, see for a1 we are getting 1 by, so 1 by pi, a2 we are getting 0, then a3 minus 1 by 3 pi, then k equal to 4 0, and k is equal to minus 1, we are getting 1 by pi. If I draw this with respect to k is equal to 0, so k is equal to 0, if I substitute, so it will become 0 by 0 form, right? So we have to use the L'Hospital rule, right? So we have to differentiate with respect to k. So sine means cos we will get. So L'Hospital rule, cos k pi by 2 into pi by 2 by pi. Now cos 0 means 1, so pi cancels, so it will become 1 by 2. So some value will be there. Then k is equal to 1, so we will get 1 by pi. Similarly 1 by pi. Here we will get 1 by 2. Similarly 2 means we will get 0 here and 0 here. 3, this is 1, this is 2, this is 3. 3, what is 3? We will get minus 1 by 3 pi. Similarly this is minus 1, minus 2. So minus 3, if I substitute, so we will get again minus 1 by 3 only. This is minus 1 by 3 pi and etc. Right? Now if you see what is the Fourier coefficients, so it's a discrete in nature, right? Discrete in nature. So remember this point. The Fourier coefficients, the AK in continuous time signals, so AK is discrete in form, right? So this is how to find the Fourier coefficients, Fourier series coefficients. Now we'll see one more example, that is x of t is given some minus 3 to 3 ak e power jk into 2 pi t, and where a naught is equal to 1, a1, and the Fourier series coefficients also given. So we need to determine what is the x of t here, right? So this is the harmonically related complex exponential. So minus 3 2 means a minus 3 e power minus j 6 pi t plus a minus 2 e power minus j 4 pi t plus a minus 1 e power minus j 2 pi t plus a naught plus a1 e power j 2 pi t plus a2 e power j 4 pi t plus a3 e power j 6 pi t, right? Something like this. See what is here jk omega naught t. So what is omega naught here? Say 2 pi. What is the fundamental frequency time period? Fundamental time period t is equal to 2 pi by omega naught. So omega naught is given 2 pi. What is the time period? So it is 1 second, right? So if I find this a minus 3 is given directly 1 by 3. So a3 and a minus 3 is given 1 by 3. So I can take 1 by 3 common. So it will become e power j 6 pi t plus e power minus j 6 pi t plus a minus 2 a2 is given as 1 by 2. So directly I can take common 1 by 2 and it will become e power j 4 pi t plus e power minus j 4 pi t. Next one a minus 1 and a1. So it will be given 1 by 4. So it will become e power j 2 pi t plus e power minus j 2 pi t plus a naught is given 1. So if you see here, this is e power j theta plus e power minus j theta. So if I take 2 here, I will make it as cos theta. So here 2 means here also 2. Again here anyway 2 is there. So here also 1 by 4 into, it can be written as 1 by 2 into 2. So it will become 1 plus, so first I will write this one. This is 1 by 2 cos 2 pi t e power j theta plus, then I will write this one. So simply this is 1 by 2 is there, so directly cos 4 pi t plus this one is written 2 by 3 into cos 6 pi t. So this is the x of t. Now we got this x of t as like this, that is 1 plus 1 by 2 cos 2 pi t plus cos 4 pi t plus 2 by 3 cos 6 pi t. If you see, this is a 1 means it's a DC component, and see here what is the fundamental period omega naught is 2 pi. That means it is a fundamental frequencies component, that is we can say first harmonic component or fundamental component, and this is, it can be written as 2 into 2 pi. So it is second harmonic component. This one is, it can be written as 3 into 2 pi. So it is a third harmonic component. That means the x of t can be represented by, it's a fundamental frequency and harmonics, that is it can be represented by complex exponential signals, right? So it can be represented by the weighted sum of the cos, right, or we can say trigonometric sums, right. So we'll see graphically how we get this x of t is a periodic signal. Now if you see here, this section of t is 1, that is a constant signal DC which is from minus infinity to infinity. Now if you see x1 of t which is 1 by 2 cos 2 pi t, cos signal means it will be at 0 means we'll get the 1 by 2 is the amplitude, and it will be varying with respect to the frequency 2 pi, right. Now if I add these two signals, what I will get, DC plus AC, will get the DC shifted version like this. So it will be shifted by how much, 1. Now the next component is x2 of t which is cos 4 pi t. So compared to 2 pi t cos 4 pi t, the frequency is high, so that's why these two are somewhat they very close in nature, right. So the number of cycles per second it will be more compared to this one, and what is the time, I mean the amplitude will get 1 here. Now if I add this signal plus this signal, so at 0 here, see if you see this is 1 and this will become 1.5, and this will become, this is 1 means 1 minus 0.5, so it will be 0.5. See at 0 it is 1.5 and 0 it is 1, so we will get more amplitude here. And similarly if I add say point by point, so we will get periodic in nature. See here, so it is 0 and it is down, then again slightly raising, so somewhat some level, then again it is falling, so again it is raising, so up to here one single period from here to here, then it will be repeated in nature. So that's why we will get the periodic signal. Any periodic signal can be represented by its harmonics. Similarly if I add one more signal, that is x-ray of t which is 2 by 3 cos 6 pi t, so which is 6 pi means the frequency is very high, so close in this what you call period, this signal, right. The number of cycles will be very small, right. So compared to this we will get 3 signals in a same period whatever here. So if I add these two signal again, so we'll get the final signal which is x of t, which is the harmonics as well as the fundamental period like this. So the x of t is a periodic signal here like this, right. So this is a proof that x of t can be represented by complex exponential weighted sum of complex exponential signals, right. So only periodic signals can be represented by its weighted sum of complex exponentials, right. Now we will see what is the convergence of Fourier series. So we cannot find all the periodic signals into the, we cannot find the Fourier series representation of any kind of periodic signals. So what is these conditions? So generally these conditions are called Dirichlet conditions. So in the previous gate exams, so many questions, few questions came from these conditions also. The first condition essentially is x of t should be periodic. So it is not a Dirichlet condition, but it is a necessary condition to find the Fourier series representation. So x of t should be periodic signal. After this, a periodic signal can be, some conditions should satisfy. Those conditions are called Dirichlet conditions. Now what is the condition 1 is, over any period x of t must be absolutely integrable. If I integrate over one period x of t, it should be finite value, right. So that is the first condition. So the one x of t which is violating this condition is this one. If x of t is equal to 1 by t, right, over one period, that is 0 to 1, see if it is at 0 it is infinity. If I integrate over this period, so we will get the integration is infinity. So we cannot find the Fourier series for this type of signals. That is the first one. So x of t must be absolutely integrable over one period. Now condition 2 is, so in any finite interval of time x of t is of bounded variation. See, that is, there should be finite number of maxima and minima during any single period of the signal. That means, see here, so it's a periodic signal, and see here, this is, suppose this is over one period, right. Now this is not a bounded variation. So bounded variation means it should be simply like this, or it may be like this, or it may be any form. The maxima and minima should be what you call finite, right. So if you see here, so sometime it is getting something like this, and so many maxima minima are coming in this single period. So these two signals can be represented by Fourier series representation, but this cannot, because this is not a bounded variation. Now if I recall here, so this type of signals are continuous time signals, because maxima minima is not a finite here, so many maxima minimas are there. But if you see this type of signals, right, see here one maxima and one this is maxima, this is minima, one maxima and one minima. So these type of signals, generally this is called digital signal, but so if it is in a time domain, so it is also called continuous analog signal. So these type of signals are analog signals. So don't worry about this square wave, so generally it is called digital. Now you can go for the triangular waveform, so it is an analog signal, right? So I hope you get the difference between continuous time signal and an analog signal. Continuous time signal, see, continuously the amplitude is varying with respect to time. Here also it is same, it's a continuous signal, but it is generally one type of signal, so there is analog signal. So that is why all continuous time signals cannot be analog signals, but all analog signals can be continuous, not vice versa. All analog signals are continuous time signals, but not vice versa, right? So what is the condition 2? Over any finite interval of time, x of t is a bounded variation. So remember, that means there should be maxima and minima of finite values, right? Finite number of maxima and minima during over single period. So you cannot find the Fourier series representation for this type of periodic signal, but for this type of signals we can find. Next one, the last condition, that is 3. Any finite interval of time, there are only a finite number of discontinuities, right? So furthermore, each of discontinuity is finite. So discontinuity means we know. So at a sudden rise, at 0, say there is a sudden rise, and here sudden fall, again there is a constant, again sudden 0. So there should be finite number of, see here, if you see, there is an infinite number of discontinuities, right? And anyway these are finite, but these are the infinite discontinuities are there. So for this type of signals also we cannot find the Fourier series representation. Again if you see here a square wave, see, so over, suppose this is a period, so we'll get this is 1, 2 and 3, only 3 discontinuities, right? Finite number, and each of these discontinuities, suppose this is 1, this is -1, so are finite. So for this I can represent the Fourier series, and Fourier series coefficient I can find. For this one I cannot find, right? So these are the 3 Dirichlet conditions to find the Fourier series representation, right? Again I am repeating condition 3. In any finite interval of time, there are only a finite number of discontinuities. So finite number of discontinuities should be there, and each discontinuity should be finite. Again condition 2 is, in any finite interval of time there should be bounded variation. X of t is a bounded variation, or there should be finite number of maxima and minima values, right? The first one is, it should be absolutely integrable over one period, right? And the first one is should be at least essential, this is x of t should be a periodic signal, right? So this is about this convergence of Fourier series. Next we will do one more problem on this, and next we will see the properties of the Fourier series in the next lecture. So this is x of t with the fundamental frequency omega naught. We need to find the Fourier series coefficients ak. So first we need to draw the signal. See here 0 to 1, this is 1.5. So 0 to 1, 1.5 is the amplitude. From 1 to 2 it is minus 1.5, and it's a periodic signal, so it will be something like this and so on. This is t, and here also it's a continuous, something like this, right? So this is a periodic signal, so we need to find the AK, that is Fourier series coefficients. How to find? Omega naught is the fundamental frequency. So what is this? It is also, it can be written by 2 pi by t, right? What is t here? See, the time period is 2, right? So omega naught will become 2 pi by 2, which is also pi, right? What is the AK? So just remember formula, 1 by t integration over single period, so x of t into e power minus jk omega naught t dt. So what is the time period t? So it is 1 by 2, and we need to integrate over single period, that is 0 to 2. but 0 to 1 and 1 to 2 amplitudes are different, so we need to split this one. So 0 to 1, what is x of t? 1.5 e power minus jk omega naught is pi, so I can represent pi t into dt plus 1 to 2 and the amplitude is minus 1.5, and it will become e power minus jk pi t dt. So this is 1 by 2 into these two integrals. So if I integrate, this is 1 by 2 and this is 1.5 means 3 by 2. E power x means e power x only, e power minus jk pi t. So I assume this is x, so it will be differentiate, so minus jk pi, and what are the limits? 0 to 1. Similarly, if you see, this is minus 1.5, so 3 by 2, again you will get same this e power minus jk pi t by minus jk pi, and limits are 1 to 2, right? Now if I substitute the limits, then I will get the Fourier series coefficient. So 3 by 2, 3 by 2 it's common, so I can make 3 by 4 as outside. So 3 by 2 is outside, means 3 by 2 into 2, 3 by 4. If I substitute 1, I will get e power minus jk pi into 1. So e power minus jk pi by minus jk pi minus e power 0 1, so minus jk pi minus of, so if I substitute e power minus jk 2 pi minus jk pi minus of e power minus jk pi into 1, so it will be 1 by minus jk pi. So what I can write from this? So 3 by 4, see here minus of minus, it will be plus, so e power minus jk pi by, see, jk pi minus, see here again it will come here e power minus jk pi minus e power minus jk 2 pi by jk pi, right? Now from this jk pi common, so I can make 3 by 4 into jk pi common, so it will become 1 minus e power minus jk pi, so minus e power minus jk pi minus of minus plus e power minus j 2k pi. I will write like this. Now if you see, this is from this I can make 3 by 4 into 1 minus 2 into e power minus jk pi plus e power minus j 2k pi by jk pi. Now if you see this second term e power minus j 2k pi, if I take like this j 2 pi k, so e power j theta, so can be written cos 2 pi k plus j sin 2 pi k. Now to find the value, suppose if I substitute k is equal to 1, 2, 3 etc. So this will become, suppose 1 cos 2 pi plus j sin 2 pi, so is always 0, cos 2 pi means 1. Similarly k equal to 2, so it will become cos 4 pi plus j sin 4 pi, always 0, again 1. So this is always 1 when k is equal to 1, 2, 3. So what happens when k is equal to 0, that also we need to see. If k is equal to 0, so this will become 3 by 4 1 minus 2, so e power 0 is 1 plus again 1, so it will become 1 plus 1, that is 2, 2 minus 2 will become 0. So for k is equal to 0, what is ak? Directly 0. Now we need to find for k not equal to 0. If k is not equal to 0, the second term will become 1, so 1 plus 1 2, so it will become 3 by 4 and it will become 2 minus 2 e power minus jk pi by jk pi. So we can stop up to here, but we can manipulate or simplify other. So if I take 2 common, so this will become 3 by 2, so 2 and this 4 will be, we will get 1 2. So this is 1 minus e power minus jk pi. If I take e power minus jk pi by 2 common in this 2, so this will become e power jk pi by 2. If I multiply these 2, I will get 1 minus plus cancel, you will get e power 0 1 minus 1 by 2 is gone, so it will become minus jk pi by 2 by jk pi. If you see from this Euler's formula, e power j theta minus e power minus j theta by 2j, so it will become sin theta. So if 2 is coming inside, So this will become 3 pi k pi into e power minus j pi by 2k into sine k pi by 2. When this is the ak for k not equal to 0. For k is equal to 0, so ak is directly 0. For not equal to 0, the second term will become 1. So that will become like this. So if I again simplify, the final answer is 3 into e power minus j pi by 2k into sine k pi by 2 by k pi. So this is how to find the Fourier series coefficients for given periodic signals. Right. In the next lecture, we'll see what are the properties of Fourier series. Right. So that we'll see in the next class.